In this video, we are continuing to talk about finding roots of equations. So the outline for chapter 4, we've already talked about bracketing methods, we talked about the bisection and the false position methods, and now we're going to start introducing open methods. So the second category of root finding algorithms is called open methods. And we can compare kind of bracketing methods and open methods and look at some of their advantages and disadvantages. So bracketing methods require a root to be bracketed, which is a disadvantage, as open methods do not require a root to be bracketed. Bracketing methods are guaranteed to converge if one root is bracketed, so they are robust, which is an advantage, while open methods, with open methods, convergence is not guaranteed, which is a disadvantage. For bracketing methods, convergence can be relatively slow, which is a disadvantage. For open methods, when they converge, they are usually very fast, so they're more efficient. Bracketing methods cannot be easily extended to multiple dimensions, which is a disadvantage. All of the examples that we saw in the previous videos were just finding a single root, while open methods are relatively easy to implement for multiple dimensions, which is an advantage. So there are 3 examples of open methods that we are going to learn in this chapter: fixed point iteration, Newton-Raphson method, and the secant method. And in this video, we're going to focus on fixed point iteration method. So we have a function g that's defined on a set V. A fixed point of g is defined as x in the set of V such that x is equal to g of x. So if g operates on the set of real numbers, then a fixed point of g is the intersection of the graphs of the 2 functions f of x equals x and g of x. So if we've got this function f of x is equal to cos x minus x, for example, we can see that it has one root on this interval shown here. We can recast this problem and say that if g of x is equal to cosine of x and f of x is equal to x, then the root, the value of x at this intersection, where x is equal to g of x, will help us to define the root. So basically, in, for example, our previous methods, we would want to, if we're using a bracketing approach, we would want to bracket this root and find this root here. For the fixed point iteration method, we recast the problem, so we rewrite the function so that we have it in the form x is equal to g of x, and then we find the point where x intersects, where g of x intersects the line f of x equals x, and then this value of x gives us the root. So the fixed point iteration method relies on replacing the expression of f of x is equal to 0 with the expression x equals g of x. So this can be accomplished by algebraic manipulation or by simply adding x to both sides of the original equation. So for example, if we have this function f of x is equal to x squared minus 2x plus 3, and we want to find the roots of that, so we want to find where this is equal to 0, we could rewrite this as x equals x squared plus 3 over 2. So now this part here is my g of x. So I've rewritten f of x equals 0 as x equals g of x. Similarly, if I have f of x as sine x equals 0, I can cast this as x is equal to g of x by just adding x to both sides. So now this is equal to my g of x. So the fixed point iteration algorithm requires a single initial guess for the root, which we call x0. The iteration proceeds by using the current estimate for the root, so for example x1 in iteration 1, as the input argument for the function g, and then the output of our function, so g of x1, is then the next estimate x2. And the process is iterated until the output, so xn plus 1, is approximately equal to g of xn. So basically, we're putting in our old estimate, we evaluate our function at our old estimate, and we iterate until the new estimate is approximately equal to g of our old estimate. So the procedure goes like this. Assume an initial estimate x0 and an error threshold epsilon s and a maximum number of iterations n. We set n plus 1 is equal to g of xn. So again, this was our old estimate. We evaluate the function at our old estimate, and that gives us our new estimate. Then we calculate our approximate relative error. Epsilon r is xn plus 1 minus xn divided by xn plus 1. So our current estimate minus our previous estimate divided by our current estimate. And then we compare this with our error threshold epsilon s. If the absolute value of epsilon r is less than or equal to epsilon s, or if n equals capital N, which means that we've reached our maximum number of iterations, then we stop the procedure. Otherwise, we repeat. We go back and set xn plus 1 equal to g of xn. And you may recognize that the Babylonian method that we talked about in the introduction section is an example of using this method. So let's look at an example. So consider the function f of x equals cos x minus x. And we wish to find the root of the equation with an initial guess of x0 equals 0.1 and an error tolerance epsilon s is 0.001. So first thing we want to do is plot the function to get an understanding of its behavior. And we can zoom in on the area where the root is. So just replotting with tighter limits so we can see where this root is. So the first thing that we want to do after plotting the function is to rewrite it in the form x equals g of x, because this is needed for the fixed point iteration method. So for this example, we can write this as x is equal to cosine x. With x naught equals 0.1, this is the output from the MATLAB function, which I will post on eClass, showing that it converges after about 19 iterations, and the root is found at 0.7393. And you can see here how this takes place. So this blue line here is my g of x, which is cosine x. This orange line here is my line y is equal to x. So I want to find my root happens at the intersection of these two lines. So I start with an initial estimate of 0.1, and I go to, this is my g of 0.1, and then as it proceeds, my next estimate is close to 1, so 0.995, and then my next estimate is here at 0.54, and then my next estimate is here at 0.8555, etc. And this continues until I find the value of my root within my error tolerance. So here, again, I said the value of the root is 0.7393, and my error, my approximate relative error is 0.007216. And you can see how the relative error changes throughout these iterations. So in this case, the relative error kind of oscillates, and then you can see that it converges to close to 0. Now, so it's important to talk about convergence for the fixed point iteration method. So the fixed point iteration converges easily if in the region of interest we have the absolute value of the derivative of g is less than 1. So absolute value of g prime of x is less than 1, close to within our region of interest, then we expect the method to converge easily. Otherwise, it does not converge. So if the derivative is not bounded by 1, then it will not converge. So in the previous example, g prime of x is equal to negative sine x, which is bounded by 1. So the absolute value of that is always less than 1. So we expect the method to converge for basically any value of our initial guess. Now let's look at another example. So consider the function f of x is equal to sine 5x plus cosine 2x. And we wish to find the root of the equation with an error tolerance epsilon s is 0.001. So we can plot the function, and we can see that there are many roots. So we'll just, in each kind of call of the method, we're only going to find one root. So which root we find sort of depends on our initial conditions, and as you'll see, it also depends on the form of the equation. So let's rewrite the function into the fixed point iteration form. So we can do this by adding x to both sides. So we get here that x is equal to sine 5x plus cosine 2x plus x. So this sine 5x plus cosine 2x plus x is my g of x. And we can implement the fixed point iteration procedure, and we'll see that this expression almost never converges, but it just continues to oscillate. So for an initial guess of minus 0.9, this is what the result shows. So the graph here on the left, the blue line is my g of x, and the orange line is my line y is equal to x. So I want to find the root is when x is equal to g of x. So that's when these two lines intersect. And as you can see, that happens many, many times. So if we were to find a root, it would depend on our initial guess. In this case, I started with an initial guess of minus 0.9. And you can see that the relative error over the iterations, it has some kind of wild oscillations near the beginning and the middle, and then it just continues to oscillate. And if you look at the numbers as they're printed out, after 47 iterations, I still have not converged. I still have an approximate relative error of, in this iteration it's 0.3, but you can see that it's oscillating from minus 0.77 to positive 0.38. So the expression f of x equals 0 can be converted to different forms of x equals g of x. So for example, if we assume that x is not equal to 0, then we could actually write this as, we can divide through by x, and then just add x to both sides. So we could say that x is equal to sine 5x plus cosine 2x all divided by x plus x. So with this new form of g of x, the expression does converge depending on the choice of x0. So for example, using x0 is equal to 5, this is the result here. And so you can see that the method converges in only a few number of iterations, and I found a root at 4.2645. And you can see what happens to the relative error, so it oscillates only a tiny amount, and then it converges quite quickly. And in this graph here, so in this graph, the blue is my new form of my g of x, and you can see that it's not defined when x is equal to 0. And then again, the orange line is y is equal to x. So this is the root that, or the location of the root that I'm finding with an initial guess of positive 5. The same example with the same form of g of x with an initial guess of minus 0.5. Now I'm finding this root at negative 4.7524. And you can see how the relative error changes over the iterations, and again, it converges very quickly. And in this case, the relative error does not oscillate at all, but it converges monotonically. So unlike the bracketing methods, this open method cannot find a root in a specific interval. The root that we find is a function of the initial guess x0, and it's a function of the form of x equals g of x. But the user has no other way of forcing the function to be within a specific interval. Typically, if you want, you can try to, if you want to get a root near a specific region, you want to try an initial guess close to that, but even that doesn't always work to force that to be the root that you find. So for example, it's very difficult to use the fixed point iteration method to find the roots of the expression sine 5x plus cosine 2x in the interval from -1 to 1. So we should spend a bit of time talking about an analysis of convergence for the fixed point method. to understand a little bit of these last couple of examples. So the objective of the fixed point method is to find the true value vt that satisfies vt is equal to g of vt. In each iteration, we have the estimate that x of I plus 1 is equal to g of xi. So using the mean value theorem, we can write what's shown here. So we can say that g of xi is equal to g of vt plus the derivative of g evaluated at some c times x minus vt. So for some c in the interval between xi and the true value vt, we can write this expression. And if you go back to the mean value theorem, you can see kind of where this comes from. Okay, so we've got this expression for g of x in terms of g of vt, and as well as the derivative at c. So we know that g of xi is just equal to xi plus 1, and we know that g of vt is equal to vt based on the fixed point algorithm. So if we replace g of vt and g of xi in this equation, then we get what's shown here. So xi plus 1 is equal to vt plus g prime xc times xi minus vt, which we can rearrange just by bringing vt to the other side of the equation. So now we've got this expression here, and the error after iteration I plus 1 is equal to capital E I plus 1 is vt minus xi plus 1. So it's the true value minus our approximation. Similarly, the error after iteration I is again our true value minus our approximation, where here our approximation is xi. So that means that we can rewrite this expression by replacing these underlined quantities with the error, and we can say that E I plus 1 is equal to G prime C times EI. So the error in the next iteration is equal to the derivative of the function at this value C times the error of the previous iteration. So that means that for the error to reduce after each iteration, the first derivative of g should be bounded by 1 in the region of interest. So if so here if the absolute value of this is less than 1, then this value is going to be less than this value. If the absolute value of g prime within the region of my root is greater than 1, then my error is going to increase with every iteration, which would mean that in that case, my method is not going to converge. So what we want is for the absolute value of g prime to be less than 1 to know that our method will converge. So now we can try to understand why in the previous example, the expression when we wrote x is equal to g of x in the form sine 5x plus cosine 2x plus x does not converge. So if we plot our function g and its derivative g prime, we can see that g prime oscillates rapidly with values that end up being much higher than 1. So here g prime is the green line. On the other hand, the expression, when we wrote the expression in this form, it converges for roots that are away from 0. And so we can plot, again, our function g and its derivative g prime, and see that the oscillations in the derivative decrease when x is away from 0, and that g prime of x is bounded by 1 in some regions. So if we're near 0, our derivative is very large, in the negative, but as we move away from that, the oscillations become smaller, and the value of the derivative becomes smaller, and it becomes less than 1 in some regions. So when we use this expression for my g of x, then we were actually able to get convergence. So just to kind of reiterate this, if the absolute value of g prime of x is greater than 1, then the fixed point method will diverge. If the absolute value of g prime of x is less than 1, then the fixed point method will converge. And so these derivatives apply in the region of the root, or the region of interest. And further, we can say that if g prime is positive, then the iterative solution will be monotonic. And if g prime is negative, then the iterative solution will oscillate. So we'll see an example of what that means. So here, this shows 4 different sort of cases for what could happen with our g and its derivative. So in this first case, g prime is positive and it's less than 1. So this means that the convergence will be, it will converge, and the convergence will be monotonic. So basically it means that my error will reduce each time, and I'm moving towards the root every time. In this case, my derivative is negative, but the absolute value of it is less than 1. So it will converge, but the convergence will oscillate. So here I'm converging, but I'm not moving in the same direction each time. I'm going kind of around. So if you plotted the relative error, it would oscillate and then converge, as we saw in one of our previous examples. So again, both of these cases converge towards the root. The left case illustrates monotonic convergence, and the right case illustrates oscillating convergence. In the lower 2 graphs here, these both illustrate divergence. So in the first one, we've got my g of x, and my the derivative of it is positive, but it's much greater than, or it's greater than 1. So that means it's going to diverge, and it's going to diverge monotonically. So if this is my x1, instead of going towards the root, I'm going actually away from the root. And on the right-hand side here, my derivative is negative, and its absolute value is greater than 1. So again, it will diverge, and in this case, it will diverge in an oscillatory fashion. So if this was x1 here, instead of going towards the root, we just continue to oscillate away, and it diverges. So let's do another example. So let's consider the function f of x equals x to the power 4 minus x minus 10 in the interval from 0 to 4. So this is what the function looks like on that interval. And you can see that there's one root somewhere around 0.8, 0.9. Sorry, 1.8 or 1.9. And the value of the root is actually 1.8556. And we want to find the root using the fixed point method. So to do that, we can consider several different forms of the function of g of x. So we're going to look at g of x is equal to 10 over x cubed minus 1. We're going to look at g of x is equal to x plus 10 to the power 1 over 4. And we're going to look at g of x equals x plus 10 to the power 1 over 2, all divided by x. So for the first one, we can find the derivative of this expression. And again, we can plot this as well. So the yellow or orangey line is the function, g of x. The green line is its derivative. And the blue line is the line y equals x. So the root occurs where these two intersect, the blue line and the orangey line. And you can see that in this region, the derivative, g prime of x, is not bounded by 1. Thus, we expect the solution to diverge for any initial estimate of x naught. And the derivative is negative, so we expect the divergence to be oscillatory. So this is the result for x naught is equal to 2. So you can see in this plot here, we're showing this is my g of x, and this is my y equals x, and you can see how these iterations sort of proceeded, and you can see that it very quickly diverges. And then looking again at the looking again at the estimate of my xi and my relative error, again, you can see very quickly that it's diverging and it's oscillating between these positive and negative values. And you can see that from plotting the relative error as well. So this shows the relative error for the first 50 iterations, and you can see that it's just oscillating, and this will never converge. Now, if we use the second expression, the derivative is given here, and we can see that, so when we plot this, we see that this is our function again, and our y equals x. This is where the root is, and you can see that the derivative is positive, and it's bounded by 1. So it's this green line here, and it's bounded by 1 everywhere near the root. So we expect that this solution will converge, and because it's positive, within the region of the root, we expect that it will converge monotonically. So this is the result with the initial value of x is equal to 5. So you can see that it converges very quickly after only 4 iterations in this case. And we find the value of our root is 1.8556. And looking at the relative error, it converged very, very quickly. So if we consider this expression for our g, this is what the derivative is, and again we can plot this. So within the region of the root, g prime is negative, and it is bounded by 1. It's bounded by 1 within the region of the root, and then it moves away from 1 as we get closer to 0. But we do expect that the solution will converge in an oscillatory manner. And you can see this is the result when we choose that x0 is equal to 5. So it took a long time. It converged very slowly. So after 93 iterations, we did find the value of our root, 1.8547. So you can see how the relative error changed as we went through the iterations. So oscillating quite a lot and then starting to converge towards the root. And again, you can see that visually here, where we start with an initial guess here, and then we are kind of oscillating around the root, and then it's getting closer and closer to, and eventually does converge to the root. So this is just to illustrate sort of the different options that we can have in terms of convergence.